Hello everyone. Today we're going to be talking about non-permissible values, or NPVs for short, for radical functions. Again, radical functions are like your square roots, cubic roots, so on and so forth. So first of all, once again, non-permissible values means not allowed values. So we need to think about when it comes to radicals, what kind of restrictions are there? So first of all, let's do a little review about radicals. Do you guys remember what this little n here represents? Or what it's called? This little number here is called the index. Now the index is very important because that tells us if there's going to be a restriction or not. The stuff inside the radical is called the radicand. And the radicand is going to help us find our NPVs if needed. So let's do a little bit more review here. Now when we talk about the index, right, n here has two possibilities. Right? We have if n is even, so if n is even, then we do have a restriction, right? The restriction is that the radicand, so radicand has to be bigger than or equal to 0 because we cannot square root negative numbers, or we cannot even root negative numbers or values. And the other case here is that if n is odd, then we actually have no restrictions, and you're going to have no NPVs. So no restrictions, no NPVs. So the only case that we really do need to worry about here is when n is even, so square root, fourth root, sixth root, so on and so forth, right? Even numbers. If that happens, then our radicand here, we need to set it to be greater than or equal to 0, which means that it's positive and not negative. So let's take a look at some examples and see how we're going to approach this. So here are some basic examples on how to find NPVs for each. So for all of our questions here, again, we're only finding NPVs if they exist. We're not solving any of these questions. So the first one, we have the square root of x plus 3. And again, we think about, okay, well, what's the index? So again, what's square root? Although we don't see the index, it's a default of 2. So you can write a little 2 there if you like. 2 is even, which means that we do have a restriction, right? Restriction means that we take the radicand, which is the stuff on the inside here, which is the x plus 3, and we're going to make it bigger than or equal to 0. Our goal here is to solve for x or isolate for x. So to get rid of this plus 3, we have to do the opposite. We minus 3 from both sides. And we get the final restriction here that x must be bigger than or equal to negative 3. So that is going to be our NPV, or our restriction, for this question. Number 2, same thing. If we were to read out loud, we'd say square root of 2x minus 10. And again, square root index here is 2. So index is even. So that means we need to set the 2x minus 10 to be bigger than or equal to 0. We need to solve for x here. So first of all, do we get rid of the 2 or do we get rid of the negative 10? Hopefully you remember that we need to get rid of the negative 10 first. Again, if you do this in the wrong order, you get totally different answers. So in order to get rid of the negative 10, we add 10 to both sides first. We get 2x is greater than or equal to 10. Lastly here, we get rid of the 2. Again, this is 2 times x. So to get rid of it, we do the opposite. We divide both sides by 2. And we'll get the final answer that x has to be bigger than or equal to 5. So that would be your restriction, or NPV in this case. Number 3, we have the cubic root of x minus 7. What's the index? The index here is 3. 3 is odd. So with odd indexes, we mentioned that there are no restrictions. So this one has no NPVs or no restrictions, whatever you like to call it. Number 4, the fifth root of 3x plus 18. Again, index here is 5. It is odd. So once again, no NPVs, no restrictions. Let's move on to a bit more advanced questions here. So here we see we have quadratics. We have it in factored form. So for example, you might have a question where you do have a quadratic in standard form, right? The ax squared plus bx plus c, and you have to factor it into this format here to figure out, okay, what are the restrictions and how do I find them? So once again, let's take a look at number 5. It says the fourth root of, in brackets, x plus 3, and then times in brackets, x minus 1. Fourth root is even, so that means we do have a restriction. So therefore we need to set it the inside, the radicand, which is the x plus 3, and the x minus 1 has to be bigger than or equal to 0. Now this part gets a little tricky for some people. So here's a method that we used in order to solve questions like this. First of all, if we think about in terms of the x-intercepts, if we have this factored form, what are our x-intercepts? Again, we just take a look at the numbers, we do the opposite versions. So that means our x-intercepts, if we were to draw a line, put it on a number line, let's say we'll have our x-intercepts at -3 and 1. So if you take a look here, x plus 3, again, if we wanted to look for the x-intercepts, it would turn out to be -3. X minus 1, if we're looking for the x-intercept, it would be at +1. We take a look at this one here and we think, okay, we have our two x-intercepts. Now we think about, is this an upward or downward parabola? Given that if I were to expand this, and if I see the leading coefficient here is positive, we get an upward parabola. So you can just draw an upward U, like so. It doesn't have to be perfect, it's just a general idea of what's happening. Now we said that this is an upward parabola, and we're looking for when it's going to be greater than or equal to 0. Greater than or equal to 0 means that we have to be above this line. So this line here, we want to be above it. So we want to go upwards. So where does that occur in our graph here? It occurs on the left over here and on the right. So the restrictions in this case, we would then write it out as x must be less than or equal to -3, or x must be greater than or equal to 1. Let's take a look at another example. So number 6, same thing. We have square root of 2x plus 4 times x minus 3. So in this one here, the radicand has to be greater than or equal to 0. Because our index here is 2, which is even, so there's a restriction. This one here, if we were to again solve for our x-intercepts, we would find out that we would have one at -2, that's from the 2x plus 4, and we'd have one at 3 from the x minus 3. Once again, we think about, is this going to be an upward or downward parabola? This once again becomes upward. And we can see here that we want it to be greater than or equal to 0. So that means it's going to be above the line. For that to occur, once again, it's going to be on the outsides. So for our restriction here, we have to write that x will be less than or equal to -2, or that x must be greater than or equal to 3. We'll do one more example where we'll have a downward parabola to see what the answer will look like then. So for number 7, once again, square root, we see here that we have two brackets. So again, we have to set the radicand, the stuff on the inside, to be greater than or equal to 0. Once again, if we solve for the x-intercepts here, we'll see that we have one at 3 from the x minus 3, and from the negative x plus 1, if we do that, we will get +1. For this one here, we see that if we expand, we get to negative x squared lead, which means that it goes downwards. So we'd have a downward parabola like so. And again, here we said that we want to be greater than or equal to 0. So again, that means we want to be above this line. And we can see that for this graph to be above the line, it happens between 1 and 3. So in this case, our restriction would then be written as 1 is less than or equal to x, which is less than or equal to 3, which shows that x is being sandwiched between 1 to 3. So our next example here is going to be pretty common on our first step on finding NPVs when we're trying to solve for equations like this. So first of all, we get to state the restrictions on anything we see, and then we need to compare them to see which one's going to be the stronger condition. So again, we're not solving the question here, we're just finding the NPVs. So we clearly see that we have two square roots, one on the left side, one on the right side. So let's find the NPVs or restrictions for each of them, and then we'll figure out which one's the stronger condition. So on the left side, we have this one over here, which is going to be 2x minus 4 must be bigger than or equal to 0. Again, we can do the algebra here, add 4 to both sides. 2x is greater than or equal to 4, divide both sides by 2. X is greater than or equal to 2. On the other side, we have x minus 5 has to be bigger than or equal to 0. Add 5 to both sides. X must be greater than or equal to 5. Now, sometimes just writing out like this isn't that clear to see which one's stronger. So what we can do is draw a number line, put 2 here, put 5 here. So first of all, if x must be bigger than or equal to 2, that means we do solid point and we go to the right, because bigger than or equal to 2 means you have to be like 3, 4, 5, 6, and so on and so forth. If x is bigger than or equal to 5, same thing, we can do this as well, and we can go to the right as well. Again, bigger than or equal to means go to the right. Now the question is, which one of these conditions is stronger? So for this one here, if you think about it, if x must be bigger than or equal to 5, then of course that's going to be bigger than or equal to 2. Or to keep the rule simple, whatever's more to the right side, if they're going both right, the one that's going more to the right is going to win. So for this one here, you'd want x is greater than or equal to 5 being the stronger condition. So number 9, another example. So let's take a look here. Once again, left side, right side, they both have square roots. So again, we look for their conditions or restrictions. 3x plus 21 greater than or equal to 0, minus 21 from both sides, and then we divide both sides by 3. So we have x is greater than or equal to negative 7. On this side, 5x minus 40 greater than or equal to 0. Add 40 to both sides, divide both sides by 5. All right, so once again, we take a look on a number line. We got negative 7 over here, 8 over here. I'm greater than or equal to negative 7. So again, solid point, go to the right. I'm greater than or equal to 8, solid point, go to the right. The more, since they're both going right, the one that's more to the right side is the winning condition. So therefore, x must be greater than or equal to 8 for this to work. Again, you can think about it logically, right? If I'm bigger than or equal to 8, then I'm guaranteed to be bigger than or equal to negative 7. But if I'm bigger than or equal to negative 7, for example, negative 5, that's not bigger than the 8. So therefore, the strong condition is always the one more to the right. And lastly, as a reminder, if we take a look here, indexes here are both odd. So again, odd index radicals do not have any restrictions. So this one actually ends up having no NPVs or no restrictions. So there's nothing to solve for here. So always look at the indexes first before you look for restrictions for radicals. All right, so that does it for today's video. Okay, I hope it helped you figure out how to find the NPVs or restrictions for radical functions. Make sure to always pay attention to the indexes because that's what's going to tell you if you need to do restrictions, and then use the inside stuff, the radicand, set it to be greater than or equal to 0, and do the algebra to find out what the restriction will be. If you found the video useful, please like this video. It helps with the YouTube algorithm to share with other people. And also make sure to subscribe to the channel and keep increasing your math knowledge. I'll see you guys in the next video. Bye.